All right, I'm joined with Professor Lee Cronin, who is a professor of chemistry, and he's at the University of Glasgow and has a fellowship at the Royal Society of Edinburgh. For those who are unfamiliar, my name is Curt Jaimungal, and I have a background in mathematical physics, and this is a podcast dedicated to theoretical physics, namely theories of everything. Here, today, we're going to analyze Terrence Howard. He had some comments on the Joe Rogan Experience as he made plenty of chemistry, even some mathematical claims. And we want to point out where we think he's correct, where we're not sure, and where we don't understand, and where we think he may be conflating or misunderstanding.
I'm looking forward to it, Kurt. Let's do it.
Walter Russell and Michael Hudak, took me under his wing and started talking to me. But he was more into the philosophy and the love that Walter was talking about. But
By the way, have you seen this before, Lee?
I watched some of it in preparation, and I watched the main part in preparation, and then the other stuff I was like, what's going on?
Okay.
So yeah.
Okay, so we're getting pretty much your unfiltered responses.
I'm fairly prepared, yeah.
Okay.
It was to rebuild the periodic table, build a new periodic table, because the stuff I had learned in college. I told the teacher, the professor, about the relationship between hydrogen on the spectrometer and carbon and silicon and cobalt. And it was like it's the same exact color, same tone, just doubled in each octave.
Okay, he's saying the hydrogen is the same tone as cobalt. What is meant by that?
It's very difficult to interpret. I don't know whether he's meaning the same color or the same kind of frequency related with it. But the thing is, there's only a fixed frequency in the electromagnetic spectrum where you see things, right? And there are repetitions in the periodic table. So, when you do flame tests, if you look at, say, sodium, you get this nice kind of orangey color. And if you have some, look at, say, copper, you'll get some green color. And so I was kind of confused. I mean, I love the kind of poetic kind of, thoughts about these things. And it seems to me that he's making some allegorical comparison at this stage, which I think is cool. But as we can get into it, I think I can probably narrate, what is correct science today? What are the actual knowledge we have about the elements? Because I think there's poetry in chemistry, and I love that. But there is also discrete numbering in the periodic table. And that's a fascinating thing, and that's well known, and chemists taught this in Chemistry 101. In fact, I'm bashing it into my son at the moment. He has a chemistry exam tomorrow. But he's still arguing with me about the definition of the element.
Let's continue.
And he was like, no, each element is the same element, and it will always be that element. And I was like, you don't see the...
Oh, just a moment. I'm going to replay.
The relationship between hydrogen on the spectrometer and carbon and silicon and cobalt. And I was like, it's the same exact color, same tone, just doubled in each octave. You'll see hydrogen sitting all the way over there by itself, but they don't show that hydrogen has the same tone as carbon.
What do you mean by tone?
Okay, so Joe is asking what he means by tone. I'm going to let him explain, and then please you explain.
Same tone, same key of E.
Yeah.
Same what? What did he say?
Same key of E.
Key of E.
So I think he's talking about some energy relationship, right?
KeV.
But it's kind of... Yeah.
I see. Okay. Like how there's GeVs. Physicists use GeV. Okay.
Yeah.
So they have the same energy?
That's what he's saying. And he's kind of mistaken. And I'll explain what that is in a moment.
40.5 hertz. The next one would be like 81 hertz. You go to silicon, it will double up and would be 162 hertz. You'll go to cobalt, and it'll be 324 hertz. You keep dividing light by 2, and you'll ultimately get back to the audible sound of it, because there was a relationship between light and color, sound and tone, matter and shape. I put...
Okay. So there's a lot to unpack here, and I think would be worth actually explaining what the periodic table does, and two really important things, and then we'll start to unpack this, because this is very poetic, but it doesn't bear any relationship to chemistry in the periodic table in a concrete sense, where we're looking at what the difference between the elements is. Of course, the elements can have different colors. You can shine light on them and so on, and they can have what's called an absorption spectrum, and they can share commonalities. So what is an atom? So an atom, probably all your viewers know what an atom is. There are protons in all atoms. In virtually all other atoms except hydrogen, there are neutrons. And then the proton has a charge, and the electron balances that charge. And so the periodic table is a count in what's called atomic number. So 1, 2, hydrogen, helium, 3, lithium, 4, beryllium. And you can keep going up the periodic table. And that is the number of protons. Now, associated with each element, you have a number of protons. You have to have the balancing number of electrons. Now, the standard kind of model of chemistry is those electrons are quite small, and they're described by quantum mechanics. But they, like quantum mechanics has discrete quanta, the electrons occupy energies at discrete quanta. And the periodic table, you have this top layer, and then you have layers going down, and they are basically tell you about the number of layers that you have of electrons, right? That's a very simplistic way of looking at it. Now, when you hit an atom with some light, the electrons get excited. So sure, those electron excitements are a function of the how much you lift the electron up, and you take the negative charge away from the positive charge, and then it'll fall back down again. And there's a really nice spectroscopy called photoelectron spectroscopy, where you rip an electron off an atom, it will then fall back down and give out light. And that's called the absorption spectrum. So if you look at the sun, you can see the hydrogen lines. They're nice, straight lines, right? It's a really nice proof, if you like, or indication of quantum mechanics. Now, the elements, they all have lots of different colors, and they can overlay, right? They can have the same color, but that doesn't mean they're the same thing and the same absorption. It just means the energies of that electron to get out of the atom are similar. And so I think that what he's doing is confusing a number of different things. Point of fact, elements are described by the periodic table, and they are arranged in the conventional periodic table in order of atomic number. And the reason why you have this box is like you have hydrogen here and then helium, and then you can go all the way up, right? And you have these shells. So the first shell is that you have 2 electrons, and the second shell you have 8, and then it goes up and up and up as you go down. You could find many different ways of arranging the periodic table, but they don't make any chemical sense. And all the elements in one kind of column have very similar properties. So you take sodium and lithium. If you were to take the metals of sodium and lithium, he talked about water, and you add them to water, they will basically react with the water. And that's why you can make lithium-ion batteries with lithium. You can also make sodium-ion batteries with sodium. They're not quite as good. And in biology, so human technology uses lithium, right, from the periodic table for batteries. But in our cells, when for all the energy in the cell, we actually use sodium and potassium. Okay, and you can see the relationship going down. And so I love the poetry here, but I'm super confused about where the tones and the colors come from. I can only surmise that he loved the absorption spectra that you can see for some of these elements. But if you look in the sun with a spectrograph, you'll see hydrogen and helium and lithium, and they're clear lines. And if you do that on Earth with spectroscopy, you do the same thing. You will never mistake carbon for hydrogen. That's impossible. You might see under certain conditions that carbon might have an atomic absorption in a similar region to hydrogen, but that doesn't mean they're the same. The elements are fixed by the number of protons. The only thing you can do to change that one element into another is alchemy. Now, luckily, you can do alchemy in a nuclear reactor or in the sun. And so, that's kind of my very short, what is a periodic table? And you can arrange them and so on. And it was lovely poetry. But what kind of worried me a little bit was this kind of allegorical analysis. People were saying, we've been told these lies. There you go. There's a hydrogen emission spectrum about the periodic table.
This is what he's referring to. That if you were to shine light on hydrogen, it would then emit light at these are 4 different wavelengths.
So you shine light on, so the light pushes an electron out into like a zero kinetic energy, like away, like free, like in orbit around the Earth. And then when it collapses back down, it gives out a color, And that color is absolutely diagnostic of the electron in that condition. And so if you look at the atomic absorption, say, of carbon, you'll see a completely different spectrum. There you go. And so you can see that you've got carbon and oxygen and hydrogen. They're not the same, right? Carbon has many more lines. Why? It has many more electrons, many more quantum numbers. And so that's...
Do you think he was saying that, look, if you were to space out carbon, so just multiply by 2, so let's just say the distance between here, this purple one in the left side is 1 unit, and then you times that by 2, so then the space would be 2 units, and this one, let's call it 2 units, so then the space would be 4 units. This one, you understand that if you were to space them out, that it would equal somehow some other chemical? Is that what you think his claim is?
I don't think so. I don't know. I must admit, I was incredibly confused. But at the same time, I thought, well, he is trying to kind of understand the periodic table in a slightly different way. And I'm, I kind of thought some time today about it. I even talked to my research team about it because it's kind of an interesting example. Like, he's just publicized the periodic table to millions of people. That's so cool. Good bit. Sad bit is kind of confused everybody because of his allegorical part. But that doesn't mean, it's not bad. It's just not, it's not correct to say that about the elements. That's not what they do.
Yes.
There is no mystery in the periodic table with respect to these numbers. We know they exist. We can measure them. That's where we've come very far. There's lots of mystery about how do we get these elements to react. And one of the reasons I am an inorganic chemist, so organic chemists just focus on carbon. They're really dedicated to using carbon because they're for drug discovery and so on. Inorganic chemists have to deal with the whole periodic table. So there's all little tricks you use in the periodic table, like diagonal relationships and so on. But when he was talking about water and beryllium reacting, I think he's misunderstanding electrochemical processes and using elements to provide energy to cause other things to happen. Of course, if you take hydrogen and you add some energy to it, you can split it into hydrogen and oxygen. In fact, anyone could do it by getting a plastic cup, putting some water in it, get 2 brass tacks, punch it in the bottom, get a 9-volt battery and on top, and you'll see bubbles. And at one electrode, you'll have hydrogen coming out, and one will be oxygen. And that's because the water's being torn apart by the electric current. This is well-known chemistry. And so there were lots of layers. I would love to have talked to him about what he meant, because it was like, he was presumably talking about inspiration and the way he was interpreting the periodic table. But it wasn't clear to me why he felt it needed to be reinterpreted and what new explanation he was going to give the world with it, right?
Yes.
Mendeleev and all these guys thought about it for years. The periodic table's been really good at predicting what happens next. And there were elements missing in the periodic table. When, there's a gap here. I wonder if there's an element with this number of protons going to be found. And then, boom, people found them. And so they went around and found all the, a lot of elements. There's a lot of elements found in different mines and things around the UK and in the US and in Russia and France and so on. So I was deeply confused, but at the same time fascinated by the response.
Yes. So for people just tuning in or just moving to this point, Terrence is clearly bright. And just when I was going through his work, at one point he mentioned something like the free algebra generated by V or generated by X, quotiented by some two-sided ideal, something like that. Then enough, in my opinion, to be classified as bright, especially if you come to that understanding outside the university. It also shows that you're super curious, which I love. And usually on the Joe Rogan podcast, he has his mind blown. That's the stereotype of the Joe Rogan podcast. But on this one, it seems like Terrence has his mind blown constantly. And that's cool, because it just means you have fervency over the ideas that you've had for years. And some scientists can be dry about their own research, even blasé. Terrence isn't, and I love that. The difficult part for me is that it then is him speaking like a fire hose, and you have to speak to ensure that your interlocutor understands, and you have to do so step by step, and then re-explain again and bring people. You have to reference steps that came before and do so in a slow manner, not a deluge. And so, well, we can get to 1 × 1 = 2 later, but let's continue with this.
I sent over Walter Russell's.
I was trying to get to that. That's what.
Yeah, it's Walter Russell's periodic table that he put together. Now you compare that to what we mental.
Oh, by the way, someone said a hilarious comment on the YouTube channel for him. They said Joe Rogan was on the Terrence Howard Experience.
Mental layoffs periodic table. You'll compare Walter Russell's to it, and you'll see something completely different. It's unwinding, and you see there's a relationship. But go back to the wiggly one. This is how I saw it more so, but as a vortex. But you'll see there's a relationship between hydrogen, carbon, silicon, cobalt, rhodium. They're all bonded. They're all sit as a middle point between two noble gases.
So what he's referencing is another formulation of the periodic table, which just when someone says periodic table, what they mean is some arrangement of atoms in some order that gives insight and explains relationships. So you mentioned before conventional periodic table. So that to me means that that implies that there are multiple periodic tables. So is that the case? Do you, as a chemist, use only one periodic table? Do you use none of them and just focus on some other form of calculation? Are you not aware of this?
No, I'm aware. So, I mean, the periodic table history is fascinating. It's a bit like, the history of any technological era or any kind of understanding science, right? I think a good example is probably pre-Newtonian gravity, special and general relativity, right? We use Newtonian physics still because it's still pretty good to get to the moon and stuff, and we can make adjustments that Einstein gave us. The periodic tables that he refers to aren't in any way, I don't want to be rude or I don't want to be disparaging because it's cool. We talk about they're not in any way in use today, right? There is no use of these periodic tables by chemists. A chemist would use a periodic table to basically identify what's called a non-metal and a metal and look at the different blocks. And we would teach that to students so they get to understand the periodic table, the relationships. Because as you go down the periodic table, you get trends, and as you go across, you get trends. Mm-hmm. And what he's talking about, these midpoints, that's just I guess I'd make reference to some kind of labeling schemes. Occasionally, people maybe in category theory, like in some areas of mathematics, you might say, I'm going to make a new labeling scheme for this thing that helps me to give insight, right? Take maybe say Stephen Wolfram using cellular automata to tell us something about physics, right? We might use those in some new way and say, hey, can we look at physical reality? And that may or may not be a robust representation of some things, and you can play with it. It's a toolbox. Here, there's no toolbox, right? It's not clear to me what these representations would do. The chemists basically use the current periodic table to understand where the valence electrons are, these electrons on the outside, and these electrons are responsible for all the chemistry that you do, right? How you do the reactions and so on. And as you get deeper in, these electrons are less boring, are more boring, except for some very special heavy ones where the electrons in the middle actually pop out and are very sharp, and they're used for colors in phosphors. They're like europium and erbium, of course, are these rare earths, and they're really good at making shiny colors, and you can use them in some kind of medical imaging and cell imaging. They're super expensive. And so that's a very long answer. So there's only one periodic table that's in use today. The other periodic tables have no use other than to explain how science kind of battled to try and figure out what was the ground truth. In the same way that when people were looking at electricity, is electricity a liquid? Is it, a solid? Mm-hmm. How do you account for static electricity in a battery and a lightning and then AC? And they realized that electricity was unified by electromagnetism. In the same way, the unification of the periodic table is periodicity that comes from filling electrons in shells and going down quantum levels. So what I mean by that is at the top of the periodic table, we would have hydrogen, helium, 1 electron and 2 electrons. There is no more electrons you can have in the valence shell at the top. When you go down a level, then you go down to lithium and beryllium and across, right, to, the first row when you have, the carbon is there and nitrogen is there and oxygen is there. You go down a level and you have 8 electrons there, right? And so you have this counting scheme, and that counting scheme is critical for understanding bonding and structure. We use it to design drugs, understand the structure of DNA. We use it to basically actually do all the toolcraft we do in chemistry today. And it's kind of the bedrock. So the reason why I'm going in such detail is important for viewers to understand. There is not a new periodic table here you can use for chemistry. It would be confusing, and none of the things we do would work. We train physicians, drug discoverers, inorganic chemists, people just doing green energy, people doing synthetic biology. They all use the same periodic table, and it works every day in the same way that Newtonian mechanics works. It may not be perfect and the absolute truth for everything, but it's really, really close.
So those things don't really exist. It's only one substance. Now, the problem is the first thing that we're able.
Okay, just a moment. He's saying something doesn't exist. I want to rewind a bit and then explain.
Between hydrogen, carbon, silicon, cobalt, rhodium, they're all bonded. They're all sit as the middle point between two noble gases. So those things don't really exist. It's only one substance. Now, the problem is
So that's where I really kind of fell off my chair because, that's just not true. So an element is defined by its number of its atomic number, right? Because the entire thing is the number of protons and electrons. Now, a given atom, an element, can have different numbers of neutrons, and they're called isotopes. And in fact, I'll give a plug for Glasgow. The isotope was discovered by Frederick Soddy at the University of Glasgow, just a few miles from here, where he was like, "Oh, I'm going crazy. I've got these elements. These elements. They have the same chemistry, but when I weigh them, they weigh differently. What's going on?" And they realized that actually there's different numbers of neutrons, and then we put together atomic theory. So no, carbon and hydrogen are not the same. The only way you can turn hydrogen into carbon is in the sun when it basically explodes. So the only way these can come one is if you were to literally rip apart all the protons and neutrons and get out the constituent quarks and gluons and make a quark gluon plasma at whatever hundreds of millions of degrees Kelvin. And so this bit was just, not correct. And I'm not sure what he's trying to say. Maybe my only thought is if he was doing it in good faith, he's either number one mistaken, which that's fair enough. We're mistaken about things all the time. Or number two, he's trying to convey some kind of acoustic poetry to say, oh, they're the one thing because they have these values equated with them. A bit like if I took a blue car and a blue Jeep and a blue bicycle, they are different things, but they are all blue.
Yes.
And maybe he was trying to say something like that.
That was my understanding. So the string theorist would say, well, hydrogen and helium and lithium, they may look different, but they're firstly all just some arrangement of protons, neutrons, and electrons. And then even further, there's some quarks and then electrons. So they're all just quarks and leptons. Even further, they're just strings, manifestations of different vibrational modes of the strings. So it was my understanding that what he's saying is that they're the same in a similar manner. Now, he's not saying the string theory is correct. In fact, I don't believe he's referenced string theory. And by the way, for the people watching, I have a string theory iceberg in case you're interested about the math of string theory. It's a 3-hour video. But that was my understanding. As for what is that unifying element or substance, I don't know what he was saying. I think he was saying it was all reflections of hydrogen or whatever hydrogen is. Maybe he calls it something else. Does that sound like what he could be saying?
I think so. I mean, look, it's a wonderful exposition in that. I mean, I saw online and there's like all the people going, wow, there's a new reality here. And there's all the haters going, this is complete gibberish. And I'm like, well, he's not a chemist, right? And he's not using chemistry to do stuff. And so what an interesting non sequitur. The reason why I'm talking to you about this is I think A, it's super interesting culturally, and B, No. There is one periodic table, and it works quite well, thanks. And the same way, you can say at one level description we're all strings if string theory is indeed correct, and that let's assume it could be like that's good. But then at another level description where we've got quarks and gluons, they're all one thing. But the fact is, the difference between a hydrogen atom and a carbon atom is 6 protons versus 1 proton.
Yes.
That's amazing, right? To actually turn a hydrogen into a carbon, you have to get at least 6 of these charges together, and you have to come up with some neutrons as well to boot to make sure you get your C12, because you want 6 protons and 6 neutrons and 6 electrons. And so that's a really hard thing to do. And you can view that these elements are like crystallized matter at this energy level. So basically, if you have infinite energy in the universe, then everything's just basically, I don't know, whatever the highest level energy description is. It could be, let's say, a quark and gluon. And then as you cool it down, they crystallize into certain things. And the crystallization is controlled by the way they interact.
Mm-hmm.
And then they collide and you produce hydrogen, helium, And the thing that I love about all of this, the periodic table, and I would be remiss if I didn't mention it, is like the elements in our body that help biology work. I mean, they were manufactured in the star as it exploded. We're stardust. And so that's kind of, for me, like, don't give up on the element easily. They're not the same thing. Something really absolutely incredible happened to produce us. A star exploded. Whereas all the hydrogen in the universe, that hydrogen probably is produced in some other processes or can be traced back to the Big Bang.
So those things don't really exist. It's only one substance. Now, the problem is the first thing that we're able to perceive is hydrogen. That's the first visible element, because before it is too dense for us to perceive it. You understand what I'm saying?
Okay, I don't understand what he's saying. So
I have no idea.
Okay.
I have no clue what that is about. Or I could speculate, but he's on a different plane of existence to me at this point.
Okay, I thought at first he was referring to how directly after the Big Bang, you couldn't see photons even because they were too high energy. By the way, this has a technical term called recombination, which means that the universe was opaque because there were photons that were constantly scattering off free electrons. So in other words, the path of photons were extremely short and they couldn't travel without interacting with electrons.
Maybe, but yeah, okay. That's cool.
Okay. So it seems to me like what's happened here, and maybe I keep this and maybe I keep this out, but it seems like someone is studying at the first or second year undergraduate conceptual level and then realizing that what was told in high school was incomplete, maybe even incorrect. Like F doesn't equal MA and M isn't just M, there's rest mass as well. And then rather than having the feeling like, whoa, this is cool, which tends to be the feeling that most physicists and mathematicians have in my experience, Terrence has taken it from this is cool to this is reflective of something covert and tendentious, and I'm going to assume there's something suspicious going on. And part of that's correct, at least to me, the suspicious part, because one of the reasons why I started this podcast was because there are 3 levels of explanation. There's level 1, which is the high school pop sci understanding, surface level, cosmetic level understanding. And then there's level 2, where you understand now the rigor, the equations behind it. And then there's level 3, where you're able to derive the equations based on the pop sci definition because you have such familiarity with the equations. Public science communication is at level 1. So you can think of Neil deGrasse Tyson is at level 1. And there's also a level 2. And so to me, you should be wary of level 1, or you should know where the person is who's giving you the information. You're obviously at level 3. Professor Cronin is obviously at level 3. And so you should just know where is the level that you're getting the information from and what level are you speaking to. Because the surface level simplistic ones can be misleading.
There's nothing wrong with what he is doing from a curiosity point of view. But what is interesting, if there is a confusion here, or if it's not allegorical and it's just confused, what he's done is picked different levels and mixed them up. And he's trying to synthesize something else. And he maybe hasn't had time, or he hasn't had confidence. And I completely understand that. Interdisciplinary science, we do that all the time. That's why, you can make fun of what he's saying here. And indeed, I'm sure some chemists do. But just imagine how difficult it is for someone who understands cell biology and string theory to try and talk to one another. And they can, when they've only got a level 1 of understanding of each other's respective disciplines, and try to dig deeper where there's a new thing that has to happen. And that's why I'm very sympathetic. But what I like to do is remove the conspiracy nature, because at high school, it's just expediency, right? My son is 16. He's doing his high school chemistry exam, and he's making fun of me because I said, you don't have to define what's an element, and he can't define it. He said, but it's not in my curricula.
Mm-hmm.
They don't ask for that, Dad.
Yes.
And he's not wrong, right? They don't ask for that precise thing. And so I think there is this kind of, this kind of a conspiracy-esque thing, and then this confusion, and then this frustration. And actually, he has the makings of a great scientist. Great scientists have to contain the frustration for being not understanding, the conspiracy that maybe they're not quite knowing what's going on with reality because reality is not giving them what they want to know, and then basically his wish to interrogate and get the information, then synthesize it over time. And it's just sometimes if, I'm quite gullible as a scientist, and then suddenly I'm up to like, oh no, of course that doesn't work. I need to do that control.
Wait, what do you mean you're gullible as a scientist?
Well, like I remember a few years ago, I was making magnets, and I thought I discovered with my team a magnet that was really hard, but it was based on carbon. And I was like, wow, I've got this magnet. It's really hard. It acts like iron, but there's no iron. It's really hard. And I was like, oh my God, this is great, because it means we can use carbon, which is really cheap, and make really hard magnets and not have to mine stuff like, all these rare earths and all this. And I was doing all the experiments. I was starting to write the paper. And then I was like, said to my team, there's something wrong here. And we took the stuff and burnt it in a certain way. And we burnt all the carbon away. So the magnetism should have gone away. But still there were magnetic flakes. And I realized what had happened is I was using a nickel spatula, and the atoms of nickel were falling off the spatula and going into my carbon. They were just gluing onto it. And nickel was really magnetic under some circumstances, and it was faking out my car. And I was like, oh, I'm so gullible. There's no electrons there. There's no magnetism. It was a nickel contamination. Damn.
I see.
And so sometimes mixing this kind of curiosity this childlike, wow, what has happened here, is a great recipe for doing science. But you then need to have the razor of reason, if you like,
and
the
rigor.
Kind of, exactly.
And calculations.
And
so I said on Twitter, I was somewhat joking but somewhat serious, that there's this phrase called "shut up and calculate," and I said, "Understand and speak up is greater than shut up and calculate." Like just greater.
100%. 100%.
However, what I didn't say, which is underneath that, implicit, hopefully, is that in order to get to the point where you understand and can speak up, you do need to go through a period of calculating. Mm-hmm. So you need to have precision with your fingers and pen and work with a concept or an equation or with coding. And otherwise you just get a misunderstanding times another misunderstanding, which unfortunately does not equal understanding, despite 1 times 1 equaling 1. So I'll give you a subtle case. So the 1 times 1 equals 1. He says the reason why that's not true is that it's not true that if you have $1 times $1, you get $1. And he's correct. $1 times $1 doesn't equal $1. However, okay, let me say it like this. $5 times $1 does not equal $5. But 5 times $1 equals $5. And so to people who are just listening in their car and they're driving, they're like, but that sounds the same. What do you mean? Well, think about it like this. If you have 2 apples and then someone multiplies your apples by 3, then you have 6 apples. Okay. But if you have 2 apples and someone multiplies your apples by 3 apples, you have WTF amount of apples. Like, it doesn't make sense. You have apples squared. It's a different unit. So $1 times $1 doesn't equal $2. It equals some amalgam, something like $1 squared. 1, by the way, dollar squared is in the brackets. But you can still have 1 times 1 equals 1 because it's unitless. By the way, I have this whole 2-hour video on natural units, which goes over the undergraduate education in theoretical physics in approximately 2 hours from a natural units perspective, and all you need is high school math.
That's absolutely right. That's a really nice way of putting it, because there's this whole idea that mathematics, the labeling schemes that go with mathematics, when you're trying to get to abstraction, you start with physical example, your $1 times $1
exactly.
or one apple, and then you abstract out, and that abstraction said, right, can I now apply my counting to, I don't know, to pounds, to tomatoes, and so on. And then as you go down and go up, it's like the process of abstraction is a way of building these mental architectures and then removing the units in such a way that you can then understand architecturally where you add them on. And there's so many things that we do that we build these architectures on. If you think about the concept of debt or interest rate, right? I think actually the concept of our economics is more proof that time is fundamental, but that's for another podcast, another day, because you're betting on the possibility space of new things you can build, right? You know, the whole concept of capitalism is to basically take capital, put it into technology and build new things, and the value of the stuff goes up. That's why the value of our economy goes up. But there's a big digression from here, but it's just a nice thing that fits into the 1 time with 1 argument. And when I saw that, I was just like, no, dude, we need to do some category theory. I was like, no, it's not even do that. It's like, it's just a simple misconception that's easily adjusted. However, I don't know if he was, I don't know what I mean. Like I'm one of my best attributes is like, I'm wrong all the time. Right. So it's just like someone pointed out to you, you're wrong because of this. And you're like, oh, actually that's right. I think people might have tried to point out to them this 1 times 1 thing. And he's like, no. And then what happens is you build in this kind of resilience, as like this resistance to the new paradigm. And again, you see this in science. And like the real scientists, if you like, are the playful ones that make mistakes and correct. That's really cool. And that's how science kind of works. So science kind of has playful ones, and occasionally they make mistakes. And then they're the people like, no, this is how it is. It's not moving. And it plays together quite nicely where you have stubbornness and playfulness. Right. And they interact in such a way that if you're respectful of one another, you can basically discover new things and also stop people discovering nonsense and say, no, that's not correct.
Yes.
Because you do critical thinking and so on. But maybe that's a bit of a digression.
Well,
I don't know.
No, it's a great point. So Nima Arkani Hamed, the physicist, said that what characterizes physicists is radical conservatism. So not conservatism, not radicalness, but both. And the reason is that Einstein, while we look back fondly and romanticize and say, okay, what he did was undo what came prior to him, that's not true. He overturned one axiom, but held the rest so fixed. Let's see, let's just get through the rest of this. Oh, and just a quick aside again. Look, if you're going to redefine 1 times 1 to equal, say, 2, the multiplication has something called a group structure. So you can't just change one part of a group structure without changing other parts of the group structure. And one way for people to understand this is you have a multiplication, and it's called multiplication, but it's technically a group operation. And you can have a multiplication table if you have a finite group. And it's something like a crossword puzzle or a Sudoku. So if you were to change just one word in the Sudoku from screen to rabbit, you can't do so without changing the other local structure, maybe even global structure. Yeah.
But
that's a good way of putting it. I like it.
As you reach into the next octave, the carbon octave, and they call that a bisexual tone, because the carbon has 2 tones to it. It has a negative side and a positive side.
Okay, just a moment. And I don't mean this to be a racy comment or like I'm making fun of either you or him, or I just don't know. Is bisexual tone something that chemists call chemicals? Like how there's spin?
No, I mean, I wonder if he's talking about being amphoteric, or the fact that carbon can be positively charged and negatively charged. I just have no clue what he was going on about. I mean, it's just like, I was like, for me, I was pretty bemused. And then when he got to this, what was your
initial reaction? Be honest.
My initial reaction, that he was on a different plane of existence that sounded really fun. and but it wasn't my plane of existence or anyone else's.
I see. And so Terry, again, like I've tried to reach out to Terry over email, and I haven't been successful, but he's invited to this podcast. So you're welcome to come on, Terry. Like, I don't want to speak of you without you being here. We're only doing so because I wasn't able to get a hold of you, and this is the closest I can get. And hopefully we can elucidate understanding for ourselves and others at the same time.
Where lithium behaves, lithium is contractive. Beryllium is contractive. Boron is contractive. But the moment you get to carbon, you balance it out. It gets to a perfect balance of plus and minus 4. So it's a double tone. Then
Okay, so chemically speaking, what do you believe he's referring to here? What is this contraction?
So he might be talking to electronegativity, right? And say that metals are losing electrons, but I have no idea. Okay. I mean, like,
okay,
he's so out with the birdies at this point. I'm just like, it's beautiful. It sounds beautiful, but it's nonsense.
Okay, that's more than enough. Thank you, Professor. Where can people find out more about you, and what are you working on?
Wow. You can find me on croninlab.com. And what am I working on right now? I'm trying to make life in the lab because that might help us find aliens. I'm trying to work on this new theory for selection, assembly theory, which is causing people to get excited about looking at selection before evolution. And I'm also trying to work out how to make chemical computers and see if one day we can create artificial chemical consciousness. But that's the most controversial thing I can come up with a juxtaposition of listening to this. But that's maybe a podcast in the future if I get anywhere, because I'm probably going to fail.
All right. Thank you, sir.
You take care.